Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video I'm going to review Nucleophilic Aromatic Substitution, in particular the addition-elimination and the elimination addition reactions and their mechanisms. Now, before you watch this video, I highly recommend, if you haven't watched them already, watching the following videos: recognizing nucleophiles, bases, electrophiles, and acids, substituent effects for EAS reactions, and the organic chemistry reactions problem-solving process. Without these videos, a lot of what I'm doing in this video might make a little bit less sense, but if you've watched these and are familiar with the concepts, then this video should be perfect for you. In most situations, benzene rings are considered to be nucleophiles due to their abundance of pi electrons. As nucleophiles, they participate in, oddly enough, electrophilic aromatic substitution reactions. However, under specific circumstances, it's also possible for benzene rings to act as electrophiles. And as electrophiles, they are subject to two types of nucleophilic aromatic substitution reactions: addition-elimination and elimination addition. Let's talk about the conditions required for addition-elimination. First, you need to have a benzene substituted with a halogen. And this is one of those rare times when you can actually have the halogen be fluorine. A lot of the times we ignore fluorine in organic chemistry. Not only do we need that halogen, but we also need to have a Y+ group that is ortho or para to that halogen. Then we're reacting that benzene ring with a strong nucleophile. And as you can see in that reaction, what we get is a substitution overall where the halogen is replaced by the nucleophile. For elimination addition, once again, we do need a benzene that is substituted with a halogen. But in this case, we also need very extreme conditions, so incredibly high temperatures and pressures. And then we need that strong nucleophile as well. Let's take a deeper dive into both of these reactions. Let's say we encountered this reaction on a test, and we were asked to not only predict the product, but also to draw the entire mechanism. How would we approach it? Well, as usual, if you've seen my reaction videos, we would use our problem-solving process. And the very first part of the problem-solving process is to write down everything we know about that first reactant. I see a benzene ring, and because of the pi bonds, I would say that the benzene ring is nucleophilic. However, I have two substituents. One of them is a halogen, or an X group, and I know those are weakly deactivating and OP directors, at least for EAS reactions. I also see NO2, which is a Y+ group, and that's a strong deactivator and a meta-director for EAS reactions. So normally, when I see a benzene ring, I do think I have EAS reactions as a possibility. However, in this case, I see two electron withdrawing groups, and I see a halogen that is para to that Y+ group. So that opens up the possibility of doing an NAS reaction because it meets the conditions for addition-elimination. Now that I have everything labeled, you'll see that I have a partial positive on the carbon bonded to the fluorine. And you may be wondering why that spot in particular is so important. Well, that carbon is especially positive due to the inductive effects of the halogen compounded with the electron withdrawing effects of resonance by the Y+ group. And I want to point out that this only occurs when the Y+ group is ortho or para to the halogen. As you can see here, when we draw the resonance structures for a benzene substituted with an NO2 group, you can see that we place the positive charge in the resonance structures in both the ortho or the para positions. So that carbon that's bonded to the fluorine is especially positive for those two reasons. And provided that we have a strong nucleophile, that is going to be the site of nucleophilic attack. In the second step of the problem-solving process, we're simply going to look at that second reactant. In this case, it's the NaOCH3 that is on the line. And of course, anytime we see Na in organic chemistry, we say, oh hell nah, and we cross it out and we put a negative charge on whatever it's bonded to. That leaves us with OCH3 negative, which is simply a strong nucleophile and a strong base. Now that we've finished identifying everything we know about the second reactant, it's time to move on to the third step of our problem-solving process, which is drawing the mechanism and arriving at our product. So what we're going to do is we're going to draw an arrow from this negatively charged oxygen to this positively charged carbon that we identified. And when we do that, that's going to create a fifth bond on that carbon. And of course, carbon can't have 5 bonds, so the pi electrons in the double bond are simply going to move over here and form a lone pair. When we draw our intermediate, you can see that we have broken the aromaticity of the ring. Why is this even possible? As usual, the answer is resonance. The carbanion intermediate is stabilized by an additional resonance structure that is possible when the Y+ group is ortho or para to the halogen, as shown here. You can see that third resonance structure places that negative charge outside of the ring on the oxygen, and we have a carbon-nitrogen double bond. This resonance stabilization lowers the activation energy needed for this reaction to happen. There's one other thing that makes this reaction possible, and that is that halogens are good leaving groups. So the final step of this mechanism is simple. The lone pair reforms the double bond, recreating the aromaticity, and that kicks off the halogen leaving group. That, of course, gives us our final product, and you can see that that OCH3 group substituted in for that fluorine. Now, there are a couple of extra things about addition-elimination that you should know, and those are what makes addition-elimination reactions even more likely to occur. First, a more electronegative halogen increases the rate of the reaction by stabilizing the carbanion intermediate via inductive effects, therefore lowering the activation energy of the reaction. So fluorine is actually going to be the best leaving group for addition elimination. Next, more electron withdrawing groups, especially when they're ortho or para to the halogen, also stabilize that carbanion intermediate. Let's talk about elimination addition next. And we're going to analyze the reaction shown here, come up with the mechanism and the products, by simply going through our problem-solving process as usual. So the first step of the problem-solving process is to write down everything we know about that first reactant. I see a benzene ring, and benzene rings have pi bonds, meaning they have excess electron density in our nucleophiles, and a benzene ring participates in EAS reactions. Now this is a substituted benzene ring. I have an R group, which is an OP activator, and I have an X group, or that halogen, and that is an OP deactivator. So again, I'm still thinking EAS. However, I have to leave the door open for an NAS reaction because I do have a halogen on the ring. Now let's analyze our second set of reactants. I have NaOH, which again, we can cross out that Na and put a negative charge on the OH, giving us a strong nucleophile and base. I also have the delta sign for high temperature, and we have high pressure. So with a nucleophile, a lot of heat, and a lot of pressure, this screams out to me, we're going to do an NAS reaction. Now that we've identified that we're going to do an NAS reaction, we can move on to the third step of the problem-solving process, which is drawing the mechanism and predicting the products. With an NAS reaction in these conditions, the first step is we're actually going to take that base and we're going to remove a hydrogen. That carbon-hydrogen bond is going to break, and that's going to put a negative charge in a lone pair on that carbon. Now, this mechanism is called elimination addition, and the first step is elimination. Elimination means we remove two things and we put a pi bond between them. So we haven't done that yet. So what happens is the negative charge forms a triple bond between these two carbons, and when we do that, we kick off this chlorine leaving group. That gives us this structure called a benzyne. It's a benzene ring, but with a triple bond. A few slides ago, for elimination addition, we saw that there were two products. So why is that? As it turns out, when the nucleophile attacks this benzyne, it can attack either side. That's going to put the lone pair on the opposite carbon. That leaves us one final step where that lone pair negative charge deprotonates the water molecule. Giving us our final product where we restore the aromaticity of the ring. Let's talk about that non-linear triple bond. What's up with that? Well, due to the extreme reaction conditions, we get this very unusual situation. Triple bonds normally have two pi bonds that are made up of two sets of overlapping p orbitals that are perpendicular to each other. In the case of this benzyne intermediate, the first pi bond is made up of two overlapping p orbitals like usual. The second pi bond, however, is made up of two overlapping but very unstable sp2 hybrid orbitals. That's why we still get this trigonal planar structure, even though we have a triple bond. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.